From the very phone in your hand to the rocks deep beneath your feet, there's a huge branch of chemistry that describes the entire non-living world. Today, we're going to dive into the absolutely fascinating science of inorganic chemistry.
So, to kick things off, a quick question for you. When you look at things like salt, metals, rocks, and water, they seem totally different, right? But what could possibly tie them all together?
Well, the answer is that every single one of them falls under the massive umbrella of inorganic chemistry. This is the science that studies the building blocks of the non-living world. And as you're about to see, it is every bit as essential to our lives as the chemistry of living things.
Okay, so what exactly is the dividing line here? What makes a compound inorganic? Well, it actually all comes down to one fundamental rule.
Here it is, the core rule. An inorganic compound is simply a substance that does not have a bond between a carbon atom and a hydrogen atom. The absence of that very specific CH bond is the key. So, put simply, if there's no CH bond, we call it inorganic.
Let's take carbon dioxide, CO2, as an example. It obviously has carbon, but notice what's missing. There aren't any hydrogen atoms bonded to it. And that's exactly why it's classified as inorganic. The same logic works for water. It's got hydrogen, but no carbon, and table salt, which has neither.
Now, on the flip side, an organic compound must have both carbon and hydrogen, usually built on a sort of carbon backbone. These are the molecules of life itself. You find them in everything from the food we eat all the way down to our own DNA. So this one distinction creates what you can really think of as the Great Chemical Divide. Let's actually put these two branches right next to each other and see how they stack up.
Here's probably the easiest way to remember it. Organic chemistry is the chemistry of sugar and stuff like it. It's the chemistry of life. Inorganic chemistry is the chemistry of salt and stuff like it. It's the chemistry of the earth.
This table here breaks down the key differences even more. So, organic compounds coming from living things are usually held together by covalent bonds. You can think of that like a firm handshake. Inorganic compounds, on the other hand, often use these much stronger ionic bonds, which are more like powerful magnets snapping together. And that one fundamental difference in bonding, it affects everything, from whether they dissolve in water to whether they can even burn. Okay, pop quiz time. Based on everything we've just talked about, what do you think? Take a look at the chemical formula for methane, CH4. Is it organic or inorganic? It is organic. And why? Well, because it follows that one big rule we talked about. It's got both carbon and hydrogen bonded together. It really is as simple as that.
So now that we've got the rules down, let's explore the key players in the inorganic world, specifically the 4 types that are absolutely 100% critical for life itself.
Seriously, life as we know it just flat out couldn't exist without these 4 main types of inorganic compounds. Water, salts, acids, and bases are the fundamental building blocks, both inside our bodies and all around us in the world. First up is water. They call it the universal solvent for a very good reason. In our bodies, it's doing a ton of work, lubricating our joints, cushioning our organs, and regulating our temperature. Without this simple little inorganic molecule, life would be impossible. Next up, we have salts, just like the sodium chloride you have on your dinner table. When they dissolve in water, they break apart into these charged particles we call ions. And these little ions are crucial for pretty much everything, from our nerve impulses firing to our muscles contracting. And finally, we've got acids and bases. They're defined by whether they can either release or accept hydrogen ions. Now, we often picture them in a lab bubbling away, but they are constantly at work inside of us, maintaining the super delicate pH balance that our cells need just to survive. So we know these compounds are essential for life, but their importance goes way beyond our own bodies. Let's take a look at how inorganic chemistry has literally built the modern world. The cement in our buildings, the glass in our windows, the fertilizers that grow the food we eat, the batteries that power our technology. All of this is the result of inorganic chemistry. Its impact is just woven into the very fabric of our daily lives.
And here you can see the true elegance and power of these structures. This is a zeolite, an inorganic compound whose complex, almost cage-like structure makes it a kind of super catalyst for big industrial reactions, like refining gasoline.
And just to bring it right back to you, the very device you might be watching this on runs on computer chips made of silicon. And that silicon had to be purified and processed using the principles of, you guessed it, inorganic chemistry.
So after that quick little tour, what are the most important things to remember about our inorganic world? Let's wrap it all up.
Okay, here's what to remember. First, inorganic chemistry is all about those compounds that are missing that key carbon-hydrogen bond. Second, the four heavy hitters that are essential for life are water, salts, acids, and bases. And finally, its applications are literally everywhere, forming the very foundation of modern industry, technology, and medicine.
You know, we often say that organic chemistry is the chemistry of life. But as we've just seen, inorganic chemistry builds the entire stage that life performs on. So I'll leave you with this question. From brand new battery technologies to advanced materials we can't even imagine yet, what parts of our future will be built by the amazing world of inorganic chemistry?